Alright, welcome to the CS1010E final. AY 2021-2022 Sem 1. Let's get right to it. Okay, first question, print. Okay, I think this is pretty self-explanatory. Print 7 times 8 modulo 3. Okay, this one 7 times 8, 56. 56 divided modulo 3, you get the remainder. So divide by 3 and get the remainder. 56 divided by 3 is around 18. And then you will have a remainder of 2. Yeah. Print 3 equals 2, not equals 1, not equals 0. Okay, so this one, let's see. Okay, by the way, you should use Jupyter. It's quite a good code editor. So what you can do is like make a few cells and you can run them independently of each other, like this. And then I can print this. So it's pretty cool. You just download Miniconda. You can run it, install it, and open it up through this package installer called Conda in your terminal, and it will run. Anyway, back here. Okay, so print this. So the way this works, right, is it's like an AND statement. So you read 3 equals 2. 3 equals 2 is not true, that's false. Then 2 not equals 1 is true. 1 not equals 0, that is true. However, since we are evaluating this like a n, what happens is obviously false and true and true. If at least one of them is false, we get false. However, if we put this true, this one becomes true. So that evaluates to true, true and true and true. If we do, let's say 1, right? Okay, so 1 is equal to 1, that's true. 1 is not equal to 1, that's false. 1 is not equal to 0, that is true. So it becomes true, false, true. This should be false. Okay. So you treat that like an AND statement, where all your expressions in there are like ANDs. And. Okay. Next. Print. Yeah, so it's false. Print. Let's see. Okay. So we get this, right? Print this and this. Or this. So this is AND. This is OR. 1, 2, 3, and 2, 3, 4. These are sets. So these are set operations. And what we do is like, actually the order of precedence, you can look this up, of set operations is, first is the AND, and then is what we call an XOR, the XOR logic, and then OR logic. So this one will be evaluated first, then this, and then this. Okay, so first we check this. So this whole expression will be evaluated as one thing, so we can do it in sections. So we check this and so what is in both of these? It is 2, 3, and 2, 3 here. So already we have 2, 3. Okay, and then we evaluate this part. 3, 4, 5. Okay, so from this first half we got 2, 3. Then we evaluate the rest of it. So we go from left to right. 2, 3, 2, 3, 4, 5. Or is just basically like an addition. So what you get is like an addition of it, but you are not allowed to have duplicates, right, in sets. So what you get is 2, 3, 4, 5. So let me comment that 2, 3, 4, 5. If I add, like, let's say 6 here, it will be 2, 3, 4, 5, 6. Yeah. Okay, moving on. I hope that's clear. Yeah. Print len. Okay, this one is just you need to check the brackets properly. So basically all this is from the function. Okay, so we are looking at these only. So we print the length of this. Is this? They want you to put 1. The problem is if it wants to be a tuple, right? It needs to have comma. Sorry, it needs to have a comma here, right here. So print A, right? It's a tuple. So if I print A plus another tuple, let's say 3. Sorry, 3. It will add this 3 to this tuple A. But so there's a trap. They want you to think this whole thing is 1, but it's not a trap. It's not a tuple. So it's just a pair of parentheses, because you need to express something in brackets as a tuple, right? You need the comma. This is a tuple. This is just 2 with parentheses in front to confuse you. So you can basically delete this, and then you have this expression inside. And then from there, what you do is you just count. So we have 1, 2, this is one thing. This one thing, and then this is one thing. So we take out the print, right? And we take out the len. And just count this. 1, 2, 3, 4. Because we're counting shallowly, we're just counting the shallow part. 1, 2, 3, 4. Okay, so that's fine. LA, list A. What does this say? This B is. Okay, the reason why is A is. Okay, so the reason why is A is. Here we assign this B to be list A, the first element of list A. The first element of list A is this list. Sorry, index 1, right? Not the first element, sorry. The index 1 is this. This is index 0. Then we count shallowly. So this is list A, index 1. This whole thing. So basically we define list B to have this. However, when we do this, right, it's a shallow copy. We're not copying. We are getting this exact same thing from list A, and this is something you have to remember about Lisa. So basically, right, whenever we change to this part, it's also going to change here. They're kind of connected in memory. Their memories, right? Memory points to the same location. So, yeah. Then this one is LA index 1, 1. So it's this part. Because we're looking at this part, LA1 is this. LA11 is this. So that's this. So we can put this here, and this one is this one. Okay, so what happens if we take 0, 1? We just make this one, right, LB01 is, sorry, LB01 is this. 0, LB0 is this. LB01 is going to be connected to this. So let's type out LB full. LB, it will be LA1, comma, LA1, 1, LA1, 1. Then right, what we're doing is look at LB0, 1. So there's this particular part. The thing is, this part and this part reference the same place in memory. So then it points to the same location in memory. Yeah. So when we change it to 9, let's say we change this to 9, right? We're changing this to 9. This is what happening to LB after this. LB is now this. We're changing that to 9. What happens here also is it becomes 9. So when we print LA, now this is LA, we modified LB, but it was printing the same thing in memory. So now LA is LA. With this one, since we changed it already to 9, we also change it to 9. And we get 1, 2, 9. There we go. Okay, next one. Print this. That's R. Okay, the reason why, let's go. It's R. And obviously we can't use a editor in exam, but it's easier to learn this way. Okay, so first we get the second index. So this is first. This is a list in a list. This is a string. All in a list. And we get the second index, which is QRS. The first, so it's QRS. Then right, we have index 0, 1, 2. We want 1. Sorry, we want 2. We want 1. So we got R. R. So if you want to print R0, right? That's just R. Yeah, it's basically just R. So we got QRS 1, that's R, the string R. Then we put 0. So if we print QRS, let's see, right? Print QRS and QRS 1, 0 is the same thing. Okay? Yeah. Now we move on. LA 1 times 2, LB LA times 2, LB this. The reason why it's 9 is pretty straightforward. So yeah, question 8 now. Here's it. Question 8. Okay, so first we have list A, which looks like this, right? Now list B, right, is a list of list A, but since list A is already a list, it's now like this, times 2. Now you see, right, if it was list A times 2, just list A times 2, it will be this. But now we have the list of list A, which is already a list. Okay, so get this. Now LB, right, is basically going to be this. We have a list with LB inside, copy of it. And since LB is a list itself, we have to put this there. And then since this LB is LB but reverse, it's basically the same thing. Okay, so we have this list and this list inside this list, and each of these have 2 lists each. Okay, okay, now so we get LB0. LB0 is this. LB01 is this. LB010 is this. Change that to 9. So now LB looks like this. Now print LB 1 0. LB 1 LB1 0. Okay, so the reason why is 9 1, right? Is because when we duplicated this thing and this thing point to the same thing in memory. So this thing, this thing, this thing, and this thing all point to the same thing in memory. So right, if you want to print LB now, it's quite funny. Let me get rid of this. It's quite funny. Because you changed all of it. So no matter what you pick here, right, you're going to get all of it 9 1. Because they all point to the same thing in memory, like here. Same thing. Okay. Moving on to number 9. Okay, print. Where's this one? Print this, right? You get this. Okay, so what I want to do is just get rid of this print statement so we can analyze it properly. So we have the list. We have a tuple. Yeah, tuple. 1, 2, 3. Then there's one element here, and then 7 element. So we want to slice it into 2, 5. So we start at index 2. So 1, 2. So I'll start from here and then go all the way to index 5, but not including it. So 2, 3, 4. You get this. Then we reverse it. So get this off. So your operations, right? You find the big fat one first. Then you look at the next on the right, and then only you look at the right. So you kind of squish it down to the left. It's like a stack. So it's like, right, and then you no, maybe it's not. Let's forget about that. Okay, number 10. Okay, so def f of x modulo 2 is 1. Okay, so we have basically a bunch of embedded functions. We pass 1 here, so 1 modulo 2 is indeed 1. And yeah, so if x is so when you modulo, right, anything that's here, if it's less than this, it will give simply that number x. So 3 modulo 4 is just 3, 3 modulo 5 is just 3, 5 modulo 10 is just 5. Okay, so here you passing 1, this is true, so you return x plus 1. So we're going to pass x plus 1, which is 2, into this second function. Now we just keep track of which functions we're in. We're in this second middle function now. So we pass 2 inside. Okay, 2 modulo 2 is 0. So else return 2 plus 4, which is 6. Okay, now we have 6. And then look here. You're going to f. Okay, 6. So we're passing 2. 6. 6 modulo 2 is not 1. 6 modulo 2 is 0. So we have 6 plus 4, which is 10. So what you do right here, when you look at this question, you should understand what is going on here first. So we understand that this is a bunch of embedded functions, right? That the result will be the input to the next function, and then we just repeat. So when we do that, we think about it first like that. It's easier to, when we keep track of what's going on, it's easier to say okay, I'm not going to get lost because I know that the next thing I do is just put this result of this inner function into the outer function. So it's not so easy to get lost that way. Okay, 11. If not x, return x. Okay. So here, right, I look at this function and I can really see this and this takes the last objects of the last elements of the object or the argument, and puts it on the sides. So I'm looking for something like this already. Something like this. This one not really, because I'm looking for something like this. And then inside, right, it will just be the same thing. So it will be stuff on the sides, and just getting smaller progressively. So it will be something like 1, 2, 3, 4, 3, 2, 1. It should be something like that. Where this one will be reversing each iteration. So how I know that is when I keep passing this, it's going to be flipped, reversed, and then the next iteration of this function, when I recursively call it, it will be flipped again, it will be forward facing. So first it will look like EE on the sides, then inside, right, is reversed, so you get DCBA. Yeah, and then basically you get this trying to speed up a bit. Okay, so this one a bit tricky. So what's going on here is just so what's going on here is, okay, you'll get G. So you're not supposed to count from 100. You're not supposed to count from 100. Obviously, you see the pattern, you short circuit. I don't think that's a term, but you short circuit. So when we pass 100 here, it's not less than 0. 100 is not less than 100. Yes, this is true. So we return G of 99. So we pass 99 here. 99 is not less than 0. 99 modulo 2 is 1. Return this. Return F98. So then we come back here. And you can see, right, we're passing in odd and even values alternating. Here will be odd, here will be even. And you return the other function. So what we can shortcut it to is just the case where we're almost approaching this case, like we're going down, we shortcut to the case, like maybe we can shortcut to 2, because we can see that it will be the same pattern all the way down to like number 2 from 100, where you're like 100 here, you input 99 here, you input 98 here, put 97, and you get 2. So you shortcut to 2. Okay, so we hypothetically say that we pass 2 here, because after multiple iterations you end up with 2. So 2 modulo 2 is 0. Return G1, 2 minus 1. So G1, 1 is not less than 0. 1 modulo 2 is 1. So return F1 minus 1, which is F0. F0, 0 is not less than 0, 0 is equal to 0. So we're going to skip this. 0 modulo 2 is 0. We return G negative 1. Negative 1 is less than 0. So we return G. There we go. Okay, this one. XY is 100, 0. If X is more than 10, X is 100, it's more than 10, so Y is now 1. So X is 100, Y is 1 now. We can skip this because it's connected to this if statement. If and else if, sorry. So they come in pairs. We can skip that because we already went to the if statement. Now we go to this if statement. So X is 100, X is not more than 1000, so Y is not 3. We go to else. Y is now assigned to 4. So now X is 100, Y is 4. Okay, XY is equal to 10, 20. This is quite simple because X is not more than 20, so we can just ignore this whole block. Else, if 2 times X is less than Y, 220, 2 times 10 is 20, it's not less than Y, because 20 is equal to Y. So this should be a less than or equals to, if so that it will be true. So this does not evaluate. Instead, we get else if 20 is more than 20, which is also not true. So this also doesn't run. And notice that we didn't actually assign z anything, because all of it was, we didn't go through. So print z is just not going to exist. So now we have the following code. X is more than 0, x possible. Okay. Okay, so this answer is actually wrong. Because notice, right, if you put in, sorry, yeah, the answer written down is wrong. If you put in 13 for an input, where, sorry, y is 13, this is correct. I say y is 13. Sorry, x is 13. I say the input x is 13. You get 1. So that is possible. 1 is possible. That is not impossible. Instead, the answer is 2. The reason is, let's look at the case where y is equal to 2. Right, so when y is equal to 2, x has to be less than 5. So we can think of numbers like 1. So first, right, we zoom in here. We don't think about this part. So for this to be even remotely true, this has to be true first, which is x can be stuff like negative numbers or 1, 2, 3, 4, 5. However, the problem with that is this else statement is connected to this if statement. So only one of these if else can run. And if x is less than 5, it is also less than 10. And this will run first. So y will equal to 4 if you run it from top to bottom. So once y is equal to 4, this if statement is executed. This won't execute, and this won't execute. Because they only execute if this if statement is false. So if x is less than 5, let's say x is equal to 3, y should be 4. Yeah, that's why 2 is not possible. So you may ask, yeah, so 2 is not possible, sorry. Okay, x is a, well, len x is less than 6, x plus bc. Okay, so we can do this without typing. It's pretty simple. You can imagine in your head. So it's not less than 6, so next iteration will be abc. You add another bc because it's still not less than 6, because it's still less than 6, sorry. So it'll be abc, bc, and then there's 5 letters in abc, bc. It's still less than 6, so we add one more, and then it exceeds it, so we stop. So we don't stop here, we stop here. Okay, next. A is 1, 2, 3, 4. X is 0. For I in range len a. Okay, so this is a bit tricky. It's a bit tricky. Okay, so A is 1, 2, 3, 4. X is 0. For I in range len a, which is from 0 to 4. So the trick that they want to make you fall into is actually I'm not sure, but whatever. For I in range len a, you iterate x plus 1, x plus equals 1. So x is 0, so now it's 1. If I is in A, I starts at 0, 0, 1, 2, 3, and not until 4. Okay. If I is in A, so 0 is not in A, so we just skip that. Okay, so next iteration, x plus equals 1, now x is 2. If I is in A, I is now 1. I remove 1. And then from now on, x is going to plus, and A is going to have its elements removed up to 3. So basically, it won't remove 4 because I is not in the range of 0, 1, 2, 3, 4. So there's no 4 in that range, in this range. Yeah. So you'll get this. XY 9990. Okay, this one is requires a bit of maths, I think. So you need to get the closest value, and you can do this by long division. On, I don't know, maybe you can use pipe. No, you can scribble on your paper long division. So what I did is x is going to increase by the same amount of 6s as y is going to, sorry, y is going to increase by the same amount of 6s, x is going to decrease. So we can divide, no, we can divide by 6, which tells us how many times that 6 was divided. It was taken away from n, 9,999, which comes out to be 1666.5. So in the loop, right, you won't take this part to take 1666 if you imagine it, because x is still more than 0 after taking 166, but it's not enough. It's going to exceed it on the next shot. So if you subtract 1666 times 6, it is 9996. So this is the max you can subtract from x. 9999 minus 9996, get 3. So if you're gonna subtract one more, and then it will be more than 0. It will be less than 0, and then this will be false. Okay, so you can add, to y 1667 times of 6, because that will be just enough. You exceed the loop at that time, and you get 1002. This answer. Okay, so x is 0, y is 1. For I is less than 7. Okay. Yeah, node is an infinite loop because continuous skips. So when you reach here, you're just going to loop back here, and yeah, it's just an infinite loop. This one, not hard. It's just that it'll be confusing. Scope. Okay. 3, 2. The reason is x is 1, 2. We pass in x to foo, so this y is actually x. You can think of it like this. Basically you assign x 0 to be 9, and then you override it with 3, so you get 3, 2. Okay, so foo y 12. 12 is not less than 0. 12 is more than 0. So y subtracts 1. And y is, so now y is 11. Y is 11. You can check. Oh, okay. Oh yeah, sorry. We didn't define it. That's fine. I got fooled also. We didn't define it. Very tricky. Okay, this one can do from here. we have a dictionary, this dictionary. Then we have we access a index, we access a key from it, because you can see this key expression, which is nested inside here. So we have to take, be easy to show, I guess. Easy to show. Yeah. Okay. So we get rid of the print. So we have this. And then we're taking a key of this dictionary. But first we have to do this operation. So 1 of this dictionary. So we get F. Then we get Z. So answer Z. Okay. These functions. Okay, this one, this is 1. So D1 is 1 mapped to F1 to G1. Then X is equal to 1. For I range 10, X is this. Print X. So what is happening here? We have two functions. We ignore that first. D1. So we have a dictionary that maps to these functions. That's quite interesting, actually. A dictionary that the values are functions. So X is 1. For I in range 10, okay. What's going to happen is it alternates. So X D1 X starts with 1. Okay, so but we do this 10 times. Okay, so X starts with 1. So the new X will be D1 1 1. Okay, what would that return? This will return D1 1, that's F1, and pass in 1. So we get 2. So X is now 2. We loop again, second iteration, okay? Now X is second iteration. Now X is D1. The new X, it will be 2, 2. Okay, so this is D1, 2, this is G1, and we add in 2 here, 1. Okay, so as you can see, the new X is 1. Because we access this first, 2. So we have a function G. This thing is G1. And then we pass 2 into it. So this is G1. You can see now, it's a function. Pass 2 into it, you get 1. So now the new X on the third iteration is G1. Sorry, D1. 1. 1. Basically, this loops again. So you can count the loops and you eventually get to 1. So DevTail list of recipe. Okay, this is a bit tricky. Especially if you don't have any paper. You should use paper when you do this. I'm going to start recording first. Instructions. The important thing to note is what is being passed on as the input the next time. So it will be this. Okay. It will be this operation done on res, the current result, which is this, and the last element of this list. So it will be 4. Yeah, so we go to the operation, which is this lambda function. This operation. And we pass in res and list, the last element of this list, which is 4. So is res, this is res, and this is 4. we flip them around, and then we get the result, the new result. This will be an empty tuple. This will be an empty tuple. This is res, and then this will be the 4. This is the empty tuple. This is 4. This is res and 4. Yeah, so 4 empty tuple. So you can see this one will be passed as this new res in the next iteration, and the next iteration will look like these inputs. Because we only pass these up to the last element, we're not including it. So we are, it's a recursive function, that's what it's doing. The operation is the same. Then in the next iteration, remember we had res and 4 here, but it switched. So now it's 4 and this. So this is res now. And then we do the same operation. This is res. Res is x. Y will be the new one. It will be 3, the new last element. So x and y are this and 3. Okay, and then you do the same thing, you put them like this. You reverse, you turn them around. So it'll be 3 and this. And what you can see, right, is this pattern. Actually, right, you can stop here, go ahead and select, because it's just the same thing over and over again. Okay, this one, bit tricky, quite tricky. But here's the explanation. Okay. Oof. Again. So what's going on is, first we have this function, lambda x, lambda z, and what it will do, right, is higher order function. So you can, the point of this representation is that you, instead of putting x, y, z and then doing this at the end, instead of doing this, is you can, it's a bit more flexible in the way that you do it later, because you can choose your inputs of z, you can choose your inputs more carefully lah. It's just a syntactical thing, but let's just agree that this and this is mostly the same. Mostly, for our case, it's the same. I just want to confuse you. Yeah, so don't worry about it. Okay, let's carry a print statement. Oh, but for that, the answer is 8. So what's going on here is that we have this long expression. But first, if you want to really score in this, right, you need to write out everything like this. Okay, now note here, this is our main thing. It's our main thing. And we start looking from the right. So how I like to think about it is, your lambda functions all starts from the right when you try and input them inside. So what I mean is, we don't start from the left and like and flatten them in, like telescope them in from here. So what we put is, what we look at is these two, and we notice that there are 2 functions here that match these here and here. So what's going on here is actually x and y are functions, and that they are passed, that, and y is going to be, that they're going to become compound functions basically. Can you see that? Because these inputs are actually functions. So what's happening is, lambda xy becomes this. X is x here represents this function, y here represents this function. Oh my gosh, it's actually quite complicated, but yeah, right? Okay, so we can simplify this. We can take these, and since it's going to be, these xy's are going to be passed into this inner lambda function as this. So what we can do is take these, and what you get is this. Sorry. Yeah, correct. And remove this. What you get is this. Okay. Yeah. So this x and y. Oh, we still have this here. Oh, we have this here outside. This one. Okay, this is right. This right here. You notice how we move this first two inputs as the xy here, and then this one is the xy here. So we simplified it to just lambda z, and then we put the xy actually in here as this x, y, x and y, x and y. Okay, the z is still here. And then we have the 3 and 4 left over. Okay, we haven't done that because we are starting from the right and then looking for the next, for its input directly on its right. Okay. So now we can pass in 3. Okay, so what happens to 3? Because now we're looking at this big one, and then 3 is directly on its right. Okay, what happens to this 3 is it gets passed as the z here. And notice we have like basically 3 components in here. 1, 2, 3. This is 1. Okay, so 3 gets passed in there. Then it becomes a function. Let me copy this. It becomes a function where the z it becomes it disappears basically and becomes 3 because the z here is this z and it takes in this 3, so this z becomes 3, and then you are just left with 4 here. Okay, so now what's happening? Now we have this, you see? Okay, so what we can do is now pass these 3, and whether you want these brackets here or not is up to you. It's fine. Yeah, I think we need this. Sorry, we need the brackets. You pass this 3 as this x, and otherwise is this x, and basically this whole function is just, you can see, right? It's just itself. It's going to return itself. So we can get rid of this. Get rid of this, and it will be 3. This thing is 3, but it's irrelevant to this. Notice that none of these letters are here. It's not a function, so it kind of disappears, and what you're left is just this. 4 times 2 is 8. Yeah, so that's kind of how it works. Okay, moving on. It's quite, yeah, lambda functions are quite important to know. Very important, not quite important. So the answer is 1. And the reason for that is you get rid of the print statement. you have f3, f1, f2, f3. And what you can do if you're very diligent is write out everything inside, but I won't. I won't. I will, sorry. Because it's too hard to do without. Okay, you can see f3 takes three functions as, okay, f3, right? It's a lambda function with 3 inputs. And one of its inputs is a function of the 2 others. So what's going to happen here is f1 is going to look like this. This whole thing, if you compare it with this whole thing, right, you can rewrite as this. This whole thing you can rewrite as f1. Inside is f2. 2. Okay? Is, yeah, it's like that. Okay. Then you look at f1. Look at f1. Takes in 2 inputs and spits out only the one on its right, x. So basically this one, right, is just f2. You see? You compare it, just compare it. Takes in these 2 inputs, x and y. Gives out x. So now it's just x, which is f2 in this case. So you get this. And now there's this decreasing pattern. F2, you look here, it spits out y only, it spits out f1 only. And then f1 spits out the one that's right, which is 1. Quite interesting. 27. Okay. The reason for this is, why is it none of the rest? Why is it none of the rest? The reason is quite simple. If you define member, you're supposed to define self.member. Because if you define member, it's only accessible within that scope. Let me show you. That's the reason for self, by the way. I don't know if you taught in the lectures like this explicitly. This is the reason for self. You need self.member. If not, what's going to happen is member is not defined here. So you need self.member so that it's accessible throughout your whole class. Now it's like a normal function. This member is only accessible in there. You need self.member. You create self.member. You get what your expected is. So it's none of this. Okay. This one. Basically, this. Quite like this. Let me see. I think there's a typo. It's supposed to be the same line. Okay. This answer should be 12, and the reason is, okay, let's look at C3. We're passing C3. Now what you can think about is all these classes are connected because they are subclasses each other. C32. So self.x, let's make a note of everything. Self.x is 2, based on this. Self.x is 2. Now we call the super in. Now we're calling this with 2. So now, keep track of everything with 2 plus 2. This 2 plus 2 is this A. And they use the same letters to confuse you. Because each time, right, this A is not this A. Because you're using this when you call it. Okay, so now it's 2 plus 2, 4. And you put this into your super 1 class up. This class, not this one. 1 class up. 1 super class up. So you pass in self.a. Self A is 4 now. self.y is 4. And then you call this super. And you also call the f. Because they are subclasses. So you get the f function. Okay, so let's keep track of two things at once. Okay. So now we call this super, because it's the superclass of C2, with a plus a. So recall this a is 4, this a is 2, this a is 2, this a is 4. So now 4 plus 4, 8. So now self.x is 8. And you just want to take the most recent one when you answer this question. Okay? Okay, so now we do f. Call that we are here. Okay, f. We called f. So we're going to return the super f plus self.x. Now recall that self.x is 8. Correct? Yes, self.x is 8. We return this also though. Self.x is 8 plus, we're going to add on this self.y. Self.y is 4. So we take this and you add them, 12. Okay. Similar to this class question that we just did. Yeah, just in general, when you do these questions, you should just try to write out everything as clearly as possible for your own sake. And yeah. Okay, so the answer should be 8. The reason is we have C3, so we call C3. C3 is f, but it's a subclass of C2, which is an f function, so that's how we can call it. So this doesn't do anything right now, but we're going to access the f. So when since C3 is a subclass of C2, right? Basically it has a def f here, the exact same thing here. So we can think of it as being part of it. That's why we can call it. So now we reference this, right? Return 3. Okay, so we keep count. 3 plus, then we look at the super, which is C1 of C2. Okay, we're looking at this one now. Super.f. Okay, here we call this. So now it's 1 plus self.g. Now g, right, is G is quite interesting because you can look at this G. You can say, oh, it returns 2, so I'm going to put 2 here. And obviously the answer is not correct. So the answer is 4 because it's this G. That's basically it. It's actually like that. Yeah. Excuse me. So we don't call this at all. Okay, now this output. Okay, so output is empty string. And then we instantiate all these variables. Q is y plus string x, so it will be a2 in a string. And then z will be a2, the string a2 times 2 times. Remember, this is x, not string x. So it will be a2, a2. So there will be no type error because it's all fine here. It's all fine here also. You can times a string by a number. So you will output plus output will be this, add 2 here, and then you add the string 3 to it, because the finally clause will execute no matter what. So these both will execute. And this. Yeah. Okay, your given tree function is the exact same functionality. So there are 3 functions, and they all extract only the unique, the numbers that are unique. Which one will be the slowest? Now right off the bat, I can see this is the slowest. And the reason why this is not the slowest is because here, right, I'm checking, I saw the list already. So this is actually assuming that it's sorted. But what if it's not sorted? This thing is going to have a hard time, and this thing is going to have an easier time. Because when it's sorted, what I can do is I just go through each element. So it takes some time to understand what this function is doing. What it's doing is checking each one, and then the one before it. Okay. So it's very fast because I check. Let's say I check this, right? 2 and 1 is not the same. That's good. That means they're unique. 3 and 2, yes, for sure they're all unique now. 4, but then when I get to here, right, 4 is not unique. So immediately, right, I can say it's false instantly. But this one, I need to iterate through each one and then compare the whole list to each one. So I need to sort. So I need to go to 1, and then I need to search. Is 2 equal to 1? Is 3 equal to 1? Is 4 equal to 1? Is 4 equal to 1? Is 4 equal to 1? And then is 5 equal to 1? And then I need to go again for the next one. 2. Is 2 equal to 1? No. Is 2 equal to 3? Is 2 equal to 4? Is 2? So it's a lot of iterations. This one only looks at adjacent numbers, and then you can iterate through. I think once is enough. Is it? Yeah. Yeah, it's just once. You just iterate through once, and then you have just a bunch of conditionals to check. So that's very good already. So actually this is O log n squared. This is O n log n, and then this is O log n. O n, sorry, the third one. And that's because you use a hash map, a dictionary, to count how many of each thingamajig is in there. And then you, based on that, if anything is more than 1, that means there's duplicates, right? So which version is significantly slowest? A. Fastest, it will be 3. Yeah. Oh no, the following code does not work. Okay. Oh no. And the reason why it doesn't work is it should be A. You should choose A instead of this. I in range n is, because what happens is it's swapping. If you take the time to understand what's going on, it's swapping swapping the out pairs, I guess. So what happens after one iteration is you get 6, 2, 3, 4, 5, 1. After one iteration, sorry. because n starts at the length of the list, and then you decrease it. So the index n, which here is j, index n here, so this j, you swap their places with I. So I starts at 0. So this is the general idea of what's going on. I won't illustrate it, but if you go again, I will become 1 in the second iteration, and n will be 4, right, or something. So basically, you swap the places of the index at 1 and 4. So instead, now it will be 3, 4, 2, 1. Okay, see how it changes. And then if you continue on, what will happen is, if you iterate through the whole length of the list for I in range n, it's going to flip back, because at this part, let's see, right, it'll be 6, 5, 4, 3, 2, 1 after this, and then you're going to get to this index, and it's going to flip with this again. It's going to flip. So you only need to actually reverse it, right? You only need these amount of steps, 3 steps. But when you did for I in range n, you're going to do 6 steps because the length of n is 6. Yeah. So you need half of it only. You know what? The rest are just wrong. So they're just wrong. Output of this code. Ooh. What is the output? Okay, before we look at the output, maybe we can think how we can determine the output without running this. So here's the thing. Sorry. Sometimes I get confused. M is going to be, in the first iteration, length of x about 20. It'll be 10. So you get the 10th one, which is one of this, but either one. You just get a single element, x of m, right? However, like, you forgot that, this part. In the ordinary list, you will be taking this element and comparing it to this element, but in the string, you're just going to take like the absolutely last and first values, and obviously this is not equal to this closing bracket. Like this is not equal to this, so it's wrong, because it's a string. Okay, I don't think it's abusing, but yeah, yeah. This is a dictionary, yes. These are just facts. So best way is CSV package, yes, because there is a CSV package. This is an integer, yes. All these you can just Google. Not that hard. Okay, the reason why, I'm just going to give reasons. So this one is quite obvious. The first one, so you're iterating over all the rows, because you need to do that. But the reason why for J, right, you don't need to do, you don't want to do, you don't want to do starting from like 0, the index 0 to its length, is because I'm iterating over the columns, and in this case I'm searching for open parentheses plus and a closing parentheses. So if I start here at index 0, then I can't search behind it. See, where else in my code I can do that now, because I don't need to start from index 0. I need to start from the first one so that I can look back and front, and then I don't want to end here, because then I can't look in front. So I need to end here so that I can look for this. Because there's no point ending here anyways. This can't be a plus. This will never be a plus. The last element will never be a plus. Because you need a closing parenthesis after that. Parentheses, sorry. Yeah. So that's what it's checking. If the current index is this, if the one before is this, and then the one after that is this. Yeah. So this is a class. Okay. I think it's quite self-explanatory, so I'll leave that. This one. Okay. So this one, the solution is okay. Let's see how we can implement the solution without looking at the solution, so that you can learn. You know, return rest. Okay. So the greatest common divisor is, yeah. So this should return 10. This should return 5, 7. Should return 1. Okay. So basically, what we should put in here is all the values from because we have these two numbers, right? So let's theoretically give 6 or 10, 7 or 4. Okay. So we need to choose the bigger number, and the reason that's true is because we need to find the biggest common multiple, right? The biggest common divisor, which is like a multiple, I guess. So you need the biggest one because you need to be sure that when you're searching from 0 to the biggest one, that you can both so you need the smallest one. You need the smallest one. So we're going to start searching from the smallest one downwards, because that way it's easier. So let's say like I have 4, right? You can start searching from 4, and then the number itself can be the biggest common divisor. So if I start from 4, what if 7 can be divided by 4 completely? Then we are solved already. So the point is we need to start with the minimum of these two numbers in this range, and then we end at 1, because we can't do 0. 0 is not a divisor. And we step in reverse, right? Okay. So the reason why we don't start from 7 obviously is because, like, if you start from 7, you want to check that if both of them are divisible by I, right? Divisible by I, then that's good. If both of them are divisible by I, so if you start with the bigger one, I is going to start at the bigger one. I is going to start 7, let's say, in this case. Then you obviously if m is 4, 4 divided by 4 modulo 7 is what is 4 modulo 7? 4 modulo 7 is just 4. Remember, if this number is smaller than this number, you'll just give this number back. So it's not going to be 0 for sure. So there's no point starting at the bigger one. You need to start the smaller one so that the bigger one can be you can even divide by it. If not, you're just dividing a smaller number modulo by a bigger number. Yeah, so yeah, we should just return I. Yes, should be 0. So all of them can be divided by 1. Let me write it in yes. A bit confused here. How does this say this? Yeah, but basically I think that's the gist of it. Yeah. Okay. So the last question. Yeah. Okay. Prime divisor and it can fully valid. So it has non-unique 2 to 3. Contingent. Yes, the next number that can divide it is going to be a prime number. Yes, that is correct. Yeah. Okay. So, excuse me. Okay, let's see how I can do this. I'm also like solving it a bit on the fly. So let's now look at the solution. Okay. Now, let's see how we can think through this. We should assume that this should return true, so we can test. We can test. Okay. Should return 3. If 1, then 1. Okay. So how we could reason through this, right, is you have a helper function and yeah. So if the divisor is more than n, we return 0. Sorry, I'll copy this. Yeah, okay. So, because, okay, we have 2, 2, 2. So if what, then we return 1. So, where did this come from? Oh, the first prime is 2. So, yeah, it's like, so here they gave us first prime is 2, so it's always going to be the divisor here. So if the divisor is n, return 0, because n divided by itself. If it's more than n, it will be exceeding already. Sorry. If what return 1. Let's see, what is this trying to tell us, right? Is if is n, right? Because n divided by the divisor will be 1. Yeah. Then n modulo div is 0. That means n is divisible by the divisor. Then what would be a good shit there? If it's divisible, else, okay, so this one I think I know what it is. You are putting n and you're incrementing it, the divisor. So we're going to start with prime numbers too. So the thing about this problem, right, is any number can be expressed as a bunch of multiples of prime numbers. So 18, for example, is 2 times 2 times 2 times 2 times 2 times 2 times 2 2 times 2 times 2, which is 2 times 2, no, 2 times 3 times 3. Yeah, that's the thing. And then 21 can be 3 times 7. 5 will be just 5 itself, because it itself is a prime number. Okay. Yeah, so we have, I think these are correct. This one is the else statement. You can kind of tell that it's incremental. Like if none of these are true, right, you're going to search for the next prime number. So for example, 10 is 2 times 2 times 2. 2 times 2. 2 times 5. Yeah, because what happens was we put 10 here, right? Then we use the helper and div. We start div is 2. So uh 2 starts with 2, so 2 is not more than n, so 2 is not more than n. 2 is not equal to n, 2 is not equal to 10. Let's say in that case where it's 10. 10, yes, it's true. So we return, we say yes, good. This is the n case. N case. It means that the divisor is equal to the number, which means we search through all the numbers until 10 already. So this is like 10 times 1. But the thing is, we can express it in terms of smaller prime numbers. So by the time we get to 10, right, we already have gone through this already. So we won't get to 10, but we'll find smaller prime numbers, which is what this is going through. So if n is divisible by n is divisible by the divisor, then we return 1, because that's a count. And then we return we check whether it can further be multiplied by the same thing. So for example, if it's 8 on the other hand, we can do 2 times 2 times 2. So once you check if a is divisible by 2, you return 1, and then we call it again just to make sure with the same div, so that in these cases it's covered. Alright, I think that's all. It should work. I can't do none. Why is it none? Wow, how did they get this? This part is the key. So where I went wrong, right, is it's not called help. It's called why is it not? Okay. Okay, so the reason why we need to do this after that is because we successfully found this, right? And then we divide by it. So let's say it's 8, right? Start with 8. It's 2 times 2 times 2. So first it will be 8. And then when we get 8 divisible by 2, it will be 4. Then we pass 8 divided by 2 for the next iteration with the same divisor. So 4 turns out to be also divisible by 2. And then you go on. So that's it. Yeah. And that is CS1010E, year 2021, 22, Sem 1. So yeah, hope that was helpful. Subscribe, because AdSense.